You ready?
Yeah, let's do it.
All right. All right. So Cooper says do it. So I was fortunate enough in my lab for one of the other classes mention the database class and that Cooper was in the class, and one of the people there actually said, "You know Cooper?" I know Cooper. And, well, let me tell you about him. Okay, so I know more about Cooper than I ever thought I would want to know. But
I'm Cooper. Nice to meet you guys.
yeah, they remember you from last time, Cooper. Don't think that like you.
Great.
All right. So, any questions from last time? Right. So we'll finish up a few slides on the historical kind of thing. So this was the introduction. Then we're going to start talking about the database architecture and content and things like that. And then we'll be shifting a little bit in the order of things from what the syllabus had in terms of topics. So I had a couple of people ask if we could move some of the things around. So, like I said, as long as we're covering databases and it's actually in the list of topics, so we're just shifting some of the stuff around. So no big deal. All right. So any questions? All right. All right. So again, kind of the historical one. Again, we'll talk about this a bit more in the next set of slides as well. All right. So early adoption of database management systems were really around hierarchy and networking. And what the reason for that, if you think about things, is we think about a lot of things in terms of hierarchies, right? So when we have data, they naturally fall a lot of times into a hierarchy structure. So at the very top, so in our warehousing environment, the very top level is all the information about a given part. And then underneath that, you have all of the warehouses where the part is stored. And then for each of the warehouses, you have all of the locations in the warehouses where you're storing the parts and the quantities associated with that, right? And if I'm going to be selling these parts or receiving these parts, right? I can picture a hierarchy where it's not all these things that I just know they're sort of related. I can look at one structure and see a full hierarchy of what it looks like, right? And it's really fast because we store them basically all together as well. So in our relational systems that we talk about at the bottom here, we store things all over the place. So relational is, as we said, kind of slower, but it's the one that is the most common. So hierarchy was a very common one. And network really never caught on. So what's a network? You kind of connect things all together all over the place, right? So I could have one thing that connects to three other things, and it just got like way too complicated to try and manage. So since nobody could understand it, I said, let's just skip it and go to hierarchy, and then obviously to relational after the fact. So relational is still the most common one that we encounter. As we kind of talked about, object-oriented, which is more class-oriented, right? And these emerging applications, so it's specific to very specific parts of the business. So, for example, in computer-aided design and things like that. So the idea here was really the concept of we want to put data and the actions on that data together. Now, if we think about that when this was really happening in the 1990s, it was a new concept and hard to think of, right? And we didn't really have the infrastructure or the experience to deal with that. But if you think about the way that we structure things today, right? You have Hadoop, you have in-database processing. Well, that's really what this was back then, and we couldn't make it work really well. So it never really took off then, but now that we have more experience, we could construct the hardware associated with that, the software to manage it better, right? You kind of repackage the old ideas and now they're like really wonderful. Right? So we have that kind of stuff. So that use didn't take off, but now that kind of in-database stuff that we're talking about in the big data world is something that we see a lot of today and is really growing. Right? Okay. Right? So we have this kind of idea of the object relational. So again, right, what do? If you have things that kind of work and kind of don't work, you merge them together and make something that really doesn't work very well, right? So they tried different of these extended things to try and bring different things together and try different things, right? So if we think back to just how IT works in general, right? A lot of it's research and just figuring out how to make something work until you keep trying, right? So if you think back to the original computers, they were slower than people doing it mentally, right? Well, if we were just said, this is never going to get any better, right? We'd still be like doing everything on paper and pencil, right? But right, the vision is once we get this working, we can refine it and make it a whole lot better, and it's going to really take off. And right, so what kind of process are we struggling with in today's world this way? That probably not this decade, right? Or maybe even not the next decade, but quantum computing. Right? So people are investing a lot to get us there because it's going to revolutionize once we get there. But all the struggles to get there are going to take a lot of work and a lot of time and a lot of effort to do that. So it's the same kind of thing from a database perspective. What we're trying to show here is that we go through a whole bunch of cycles. Right? Try different things and ultimately we get better in the process. So when we look at things, right, so we have a lot of things around XML, right? So in the, probably up until maybe even 10 years ago, like nobody used XML at all in relation to databases because it just didn't work, right? You know, it's like, you want to do what? XML database? This isn't logical, right? And now we use it all over the place. So we, from a historical standpoint, we continue to add on in that. Okay. And other things is that, right, the concept of what we do and how we do things with databases. So data, right, so again, what's the difference between data and information?
Data is fact.
Data is a fact and information is taking that fact and making it meaningful in some way, right? So you think about the web, all the e-commerce applications, how things work and how much data is moving around. We talked about the autonomous vehicles and how much data each one of those is going to produce, right? We have to come up with ways that all of this stuff is going to work, and it's got to work really fast because none of you are willing to wait any amount of time for a response from the computer system. Okay. But the flip side, right, when we do some of our analytics, right, we are running against all these different databases and the single program is running for weeks, right? So you think about how fast your computers are today and it's still taking us weeks to get it done. And it's just an incredible amount of data that we can now process. But it still takes a lot of time. Right? So the good news is I start stuff and walk away. But I did have one scenario where I came in on a Monday morning and I looked to see the job that I had submitted a week and a half earlier and it was no longer running and I expected it to be running for another week. And I looked out there and it had been canceled and they said, this is running too long and we don't know what, we thought it was in a loop that was just going to run forever. And I go, no, there's this big note at the top, don't ever cancel this job. So I had to restart it and it was really great. So, but again, the point is that, right, we have to, all this data, and we have to put it someplace, and we have to retrieve it fast, and we have to do a lot of stuff with it. So, data from the e-commerce perspective, from putting it on the web, being able to build out applications that are going to be around this, and ultimately deliver it to lots of different devices, all have to play into this. Okay. Scripting programming languages, right? So PHP, JavaScript, right? So, right, we have to embed some of this stuff. So in our next set of slides, we'll be talking about how the heck do you get to it, right? So we talked in our first thing that we can create databases, and it's got data out there, and we relate some data to other data, and it's really great. Yeah, but how do you get to it? What do you do with it? We have to build wrappers around it so that we're able to actually get to the data and turn it into that information that we've been talking about, right? So, right? So we have different ways to go approach that. Right? And as we talked about, right, is we have evolving processes, right? So new functionality in terms of applications, and as we said, XML, different storage techniques, right? So again, right, a lot of what we are dealing with now that we've never really had to deal with before was images, videos, right? Streaming of data, not just receiving some data off of some web page, for example, right? So we have to come up with ways to do things real time, because again, what is going to happen in an autonomous vehicle? You can't get the data and 5 seconds later decide what to do, right? You have to analyze everything that's going on from every direction and make decisions, right? So it's lots of data, fast access, fast processing against it, make determinations, and it's complex work. Okay? So just trying to get there is going to be a big thing, right? And so audio and video, as we talked about, also we had data warehousing and data mining. So what was warehousing again? Yeah, putting it all together, lots of stuff, right? And it's got to be all those things that we have for whatever the company is. So, right, if you are a bank, you're going to have all kind of financial information about not only customers, what you need for regulations, the SEC and all this kind of stuff, right? And you have to be able to access it in all kind of different ways. And you have to keep it for a long time, right? So I was actually just telling Mark earlier when he came up here, right, is that I got a request on Friday to find some data from 1996 to 2002. Well, I just don't happen to have it like kind of sitting around, right? Because you can't keep everything on a database forever. You have to move it off and you have to archive things and stuff like that, right? And of course, it was on a system that I didn't work on. And they just go, well, we think you can find it. Okay, great, right? It took me like 6 hours, but I found it. And I go, okay, it's all yours. I'm not going to deal with it because they didn't have the layout, but the data was there, right? What's data mining? Extraction, right? And coming up with insights, right? So mining isn't just going out and saying, I need this data, but a lot of times you are mining to come up with, I have this data and I'm going to put some meaning around it by coming up with, what can I do with it? What ways can I switch looking at it to make determinations of things? Okay, so how's that all going to work? Okay. And time series and historical data. So if I was to ask you, if you were an economist, how many years of data at a company would you want to save? And the answer is not, even though it's my slogan, all data for all time, right? Right. What would be the typical answer?
Tomorrow,
No, how many years of data?
next year. That's what they all want,
No.
right?
How many years back? And see Cooper's trying to like mess with me of flipping it around. Well, if you were in the future, Right? But most companies would want 75 to 100 years worth of historical data. Why? Because you want to see all the economic cycles, right? And right, if you have 25 years, you may get one, maybe one and a part of a cycle. Well, if I'm an economist, I want to go back and look and say, what are all the different factors that go into the historical economic cycles, right? Well, guess what? We didn't have computers 75 years ago, right? So how do you get this data and how do you maintain it and where's it going to go? And right, so we have lots of things because again, not only are we generating lots more data, but we want to keep it for a longer period of time. And so how do we manage that? Okay. So the point is that we have lots of research and development. We have processes of going through and defining data, retaining data, putting different things on it, right? And you come up with different uses for it, and we're continually evolving as we work our way through it. All right? Okay. So as we talked about, right, we have search engines. So how fast do you expect Google to respond to your request when you do a search? Instantaneously. How many web pages do we have to search through to determine the search list that you come up with? Billions, right? And it's not small number of billions, it's large number of billions, right? So we, again, the more data that we have, the more that we maintain, the faster we expect things to come back, and right, how do we make that all happen? So we have to come up with new technologies that are going to do that. Right? If you think of from a social media standpoint, Facebook, Twitter, all that stuff, right? We have millions of transactions a day that we keep. And you have to be able to go back and you pull up somebody's data, you want it instantaneously, right? And you get mad when you see the little timer going and nothing coming back. And it's been 3 seconds. Oh, this is so long. What's wrong? Right? Well, there's lots of stuff to go through. Right? Okay. And it's really amazing. So when the thing that I always like is if I ask a user how long they're willing to wait for something to come back, and I say, how about 5 seconds? Yeah, that's okay. Right? You put them in front of a screen and they click on it and you count 5 seconds and they're like angry because it took too long. Right? So 5 seconds doesn't sound like a lot till you get in front of a screen and you are waiting. Right? So again, managing our expectations on all of this. Right? And again, kind of the cloud and backups and all that kind of stuff, right? So unlimited amount of storage. Yeah, well, unlimited in a theoretical sense, but in a practical sense, we always do have limits, and there's going to be cost to it. And right, ultimately, if you're storing all this data, there's a cost. So where are you going to put it? Who's going to manage it? Right. So what is, for example, your risk if you put it into the cloud?
Deleted.
Somebody other than you is managing this. So you're relying on them for security, you're relying them on for backup, you're allowing, right, you are requiring instant access to what it is, but it's no longer under your control. So that's got its good points as well, right? Because you don't have to manage it. Somebody else is managing it. They're managing the licensing of the software. They're licensing the servers, right? But again, they're in business to make money, right? So they're going to charge you for that, and they're going to charge everybody else. And ultimately, at some point, it's going to be you versus somebody else, and who's going to pay the money to do this. So it works well now, but not necessarily a great for the future. Okay, so we talked about big data before, right? So different types of storage. We talked about Hadoop and our ability to do the not only SQL kinds of stuff, right? So again, what's the different types of data, right? So I explained to you last time the problem that we're having with Hadoop is just getting the data into it. Once it's there, it's going to be great, but it is taking us, right? We have been working on a project to get the last 15 years of historical data into Hadoop, and we have 0 into it because we can't make it work. So it's not, oh, you just magically put it there. Sounds great, right? Every week my boss goes, "You make any progress on that?" No. We've had meetings on it every day this week. We're trying stuff. Doesn't work. And I can get it there, but right, the issue is that to do that same process to get all 15 years is going to take me 4 years to get it there. Yeah, so things work, right? So again, we keep trying things. So point is that we are constantly extending things, but all that new stuff comes with a cost that we have to ultimately come up with new ways of doing things. The way that I've done things in the past doesn't always work. Okay? So just managing that kind of stuff. Okay? Right? So as we talked about when not to use a database management system, right? So like any other software, there's a cost. And sometimes it's a huge cost. Right? So data warehousing using kind of the Teradata platform. So Teradata databases, Teradata Access, all that is a huge cost. In fact, it's so big that we are looking to migrate it off to some other platform. But guess what? Because everything we have is, from a warehousing perspective, is in that, it's going to be a huge cost just to migrate it. Right? So now you're playing the, do I really want to do that? Right? So you have overhead for security, concurrency control. And what's concurrency control? Two people trying to get to the same thing at the same time to do updates and stuff like that. Okay. Recovery. Oh, are you going to go with no backup, no recovery? I don't think so. Right? Okay. Data integrity. Oh my God. So, what's integrity about?
Not changing the data, just keeping it the same.
You want the data to be correct. Not part of the time, all of the time. Right? So we're managing things from an integrity standpoint. So that typically means what? You have to edit all this stuff up front. What happens when you edit things? No. It's what? No, you're trying to prevent errors, right?
So there are concurrency issues when you're trying to edit things?
Yeah, have concerning thing, but I'm more concerned about if I have to edit every field to make sure that is correct, it's going to take time. And what are you not giving me? You're not giving me time because you want it really fast. So there's always, the point we're trying to make is that a lot of times when we're dealing with databases, we are dealing with trade-offs. You have a trade-off of, I can make things better and higher quality and ensure everything's going to work, but it's going to take time and you want it faster. Well, to do it faster, I have to cut things. What do you want me to cut? I don't want you to cut anything. So that doesn't work. Right? So we always get into these philosophical things of you get what you ask for and there's risks. It's not fast enough, so people are going to walk away. Okay? You don't want that to happen. I don't do all of the edits to make sure that we have the integrity of the data and we have bad data, and now it takes a lot of time to fix it. There's a huge cost to that. So we have had, I've been in several situations where we had integrity problems with data on databases, and typically it took us 8 to 12, sometimes 16 weeks of work on it full time to correct stuff. Just because once it's there, then it starts spreading. Right? You start using it in all these other things, and you have to correct what they do, and it gets out of hand. Okay. So if the database and application are simple, well-defined, not expected to change, okay? If access by multiple users is not required. So again, a lot of times we make databases because that's just what we do. A lot of times it's simpler not to, but we do it that way anyway. Okay? And sometimes it's just infeasible. Right? So when you're doing embedded systems is the example that they give here. And what's an embedded system? It's integrated as part of some process. So you have embedded systems on your engine, for example, right? Well, I'm not going to have a whole database management system running in every vehicle, right? It just isn't going to make sense to do that. So different ways and different processes to look at that. Okay. And what was real-time requirements? What was real-time again? You're sitting there staring at the screen. You are clicking on the web page. You expect instantaneous response. Right? So we will be talking about some of the ways, because we can build databases that are strictly for online access. We can also build them for batch processing. And what was batch processing about that we talked about last time? You group a bunch of stuff together and you process it all at once because it's going to be more efficient to do that. Okay. So we have different ideas that we do in the background of that. Okay. And again, a lot of times we have different operations that we literally cannot do in the database environment because again, you have to have the supporting tools that we have associated with that. Okay. Okay, so the next section, or the topic number 2 that I have from a slide set perspective is database system concepts and architecture. Right? So the key thing that we want to talk about in terms of this is modeling. Modeling is extremely important when we talk about databases. Because what is the data model? Part of a company and potentially all of the company. Your data is important. So a key piece that is lost when most people deal with databases is understanding of the data itself. And I will contend that you cannot build an efficient set of databases or structure them effectively if you don't know what the data is and how it is used. If I build a system that is designed around batch processes, but my usage is real time, it's not going to work very well. It will work, but it's not going to be very efficient, and people are going to be mad because it's not doing it in a way that it's intended. If I have to continually make changes to the databases because I didn't think about what the possibilities are and what the data is and how the data is used, I'm going to have a very poor design at the end of the day. The most efficient thing that you can do is, before you create any databases or use databases, is understand the data. And what I tell most people is that your first task when you go to work anywhere, or if you switch departments in the company that you're at or anything else, is you need to understand the data and the processes so that if you're now going to go and automate any of that, or you're going to use the data associated with that, that you're going to be able to do it effectively. And most people don't. They will come out, even after being in areas for years, they ask, where is this data? Do we even keep this data? What data do we have available? I want to do this process. Do we do this process? Is it somewhere? Don't know, right? And it takes a lot of time, right? So it's not that you're going to remember every last little detail, but it's really important to understand all the data and how it's used. And I will tell you, in the position that I was in before my current one, I was on the same application for 17 years. And most people stay on their rotations for 3, maybe 4 years max. I was there for 17, and I was still learning more about what we did and how it worked, even at the end. Things are just so big, so huge, so much data, right? So, like I said, right, that application had 550 plus databases. We had 68,000 variables that we were dealing with, right? So continually learning always new stuff about what it is and how we do it, because again, it's changing over time as well, right? So we are looking to build models. And in this case, because it's databases, we are going to be building data models, right? And so a data model is a set of concepts to describe the structure of a database, the operations for manipulating those structures, and the constraints that we need to put in place, right? So again, if I don't understand the data, how am I going to do that? Or not? Right? Okay. So our data model structure and constraints, right? So the constructs are used to define the structure itself, right? We're going to have elements, right? And these elements are sometimes called attributes, they're called field data, they're called characteristics, right? You can have all kind of different names. It depends what company you're at, what book you have, what instructor you have, it doesn't matter, right? But it's just a piece of data. So it's a fact, right, that we're managing. And we need to understand our data type. Right? So in school, when you took all of those wonderful programming classes that you probably took at some point in time, right? How many data types did you use? If you're using something like Java or C++ or something like that, you probably used something cool like an int, right? You used a double. You used string. You may occasionally have used character, right? And that's about it, right? But why do we have all the other data types that come with that language? Because our data doesn't always fit into those very simple categories. In school, yeah, everything's going to fit into those, right? But in real life, right, so in my example, right, is I need to be calculating things out to the 28th decimal place. That doesn't quite fit into a float or a double. But that's the accuracy that I need. So I need to understand not only what the data is, but what is the data types that I'm going to need associated with that. Right? And what about the idea of images or videos? Oh, that's not an integer, it's not a double, it's not a character, right? So we have things that are blobs, binary large objects, because a picture is just a set of ones and zeros, bunch of them, that are going to describe a picture. Right? So we've had to, in some ways, create new data types that you aren't used to because we're storing different types of data. Right? Right? So we have CLOBs, so character large objects. Because we have so many characters, it's not going to fit in the normal string type of variables. Right? So again, we continually make changes to our database management systems because our data continues to change. Okay, so not only do we have to do elements in their data types, we have to group them together. So we have entities, which are things. It's very simple. Entity is a thing. Okay? So, Cooper, did you do your homework assignment?
Depends.
I asked you to go someplace and ask to see your account.
I didn't do that, no.
You're gonna do that for next time, though, right?
Oh, yeah, definitely.
Okay. It is interesting to see their reaction when you tell them that what they're showing you is not your account. It's interesting. No, we actually did that as part of the undergraduate database class, and they all came back and they thought it was hilarious. So, and based on what I've heard about you, I think you would too. Okay. All right. So entities are things. A record is basically your row of data, right? So grouping of logical data, table, a group of instances, or these records, right? So we have relationships. So, right, we want to think of it in terms of we have things and we have things that are related to each other. So we talked about that last time, right? So we had students taking a course being taught by an instructor, right? Course being offered by a department is being part of the university, right? You can have all kind of stuff, right? So we need to understand that. Okay? And our constraints specify some restrictions on the valid data, right? So these constraints are enforced at all times, right? So what might be a constraint that we have here at school in scheduling this class?
Number of students.
No, I think it's pretty.
Can't teach.
It's what?
Maybe two teachers, two faculty can teach.
No, right? Make it even simpler, right? But you're right? So if it's going to be an instructor, for example, what does it have to be? Someone has to be the instructor in the instructor or faculty instance. You can't just say, Mark is going to teach the class. He could.
You could say that.
Could say that.
Yeah.
But it's not going to probably go very well because you would not get paid since you're not on faculty. Well, I don't get paid very much either, so it's okay. Right? But what do we have here? You're in a room. I can't assign you to a room unless it exists as a location on campus. Right? Okay? When I go to give you a grade at the end of the semester, which I'm sure at this point you are all getting an A+, and you can only go down from here. Right? I want to give you all A+, but we'll see. Right? When I go to give you a grade, I can't give you a grade of a
Q.
Q. Why not? I am restricted, right? There are only a certain set of grades I can apply because there's a constraint on it. Well, what does that mean? Okay, when I go to enter that, there has to be the request that goes out that checks against that constraint. Well, if I have to do that for every single field, it's going to take time, as we talked about. Okay. So we have what we call data model operations. So operations are used for specifying database retrievals and updates. Okay. So what's a retrieval? going out to the database and extracting the data and bringing it back, right? And what's updates? Going and making a change to something, right? So we have restrictions on things that we can change. You actually have restriction or can have restrictions on what type of data that you can actually return. We have ways to speed up accesses. We have, if we do too many of those, we actually slow everything down instead of actually updating. Okay. So our accesses are faster, but our updates are slower. Right? So again, the concept is that we always have these trade-offs. Right? So what is an index? I know you've used an index sometime in your life. Right? You look in the index and it tells you where to go to get exactly what you were looking for. Right? Okay. Well, a lot of databases have indexes. And I build my indexes off of things I want to inquiry on. Right? So, what would be a common inquiry for you as a student to find information about you? I could type in your student number. Right? I may type in your first and last name. I may want to search the student directory for city, right? I mean, you can come up with all kind of different ideas. And if I build a index for every single one of the things I want to search on, what does that mean? Every time that I would do an update, I now have to check for every single index that I have out there, do I have to make a change to that index? So say I have 30 indexes. You have to go out and update the data, and then I have to, before I can say that I've completed it, I have to search all 30 of the indexes to say, does this one change? No. Does this one change? No. Does this one change? No. Does this one change? Yes. Then I have to reorganize it because I have to keep it in order, right? And all of that is taking time, and then the person at the other end is pounding their fist on the table saying, how come this is so slow? Right? So again, we have to measure these things and again, decide on what the trade-off is that we have associated with that. Okay? So we have operations on data model, including the basic operations of insert, delete, update. We have user-defined ones that are going to go out and, for example, do calculations on things, right? So idea is that there are, just like you have primitive data types in a language that come with it, and you can have user-defined formats that you can create that are based off of the primitive ones. We have the same things here. We have primitive or generic ways to do insert, delete, and updates, but I can also do calculations, right, and processes against that as we work our way through. Right. So if we look at the categories of data models, right, so we have the three that I would be looking for you to be able to describe to me are the conceptual, the physical, and the implementation. Right? So the conceptual is really high level and semantic. And what does semantic mean? It's meaning. Right? It's what the meaning of these things are. Right? Okay. Okay. So what you're trying to do here is you are trying to provide the concepts that are close to the way that the majority of your users are going to perceive things. Right? Okay. So again, the idea is my application has 550 plus databases. The user has no concept that there's that many. They get that we have a customer and we have a vehicle and things like that, right? So if I was to go to my business customer and say, how many databases do I have? They'd probably come up with 15. Well, to do what we really need to do, I need a lot more, right? But that's what we mean by the conceptual, right? It's a high-level view based on what the customer thinks, and that's okay because who is giving us requirements on making changes to our databases? The customer. And yeah, I can take what they tell me and then figure out the real details, but I certainly don't want my customer coming in and understanding all of them and telling me how to do my job. That's not happening. Right? Okay. So it's entity-based or object-based data models because those entities or these objects are the things that we are looking at from a conceptual perspective. Right? Now, the opposite kind of is the physical, this low-level or internal data models, right? So how is it actually stored in the computer system, right? Okay, so this is what is in the database management system. So where did we call that place where all of that was really stored in the database management system?
Catalog.
Catalog, or what's the more generic term? The metadata, right? Okay. So Cooper obviously has to be a little bit different than the rest of us, but that's okay, right? Okay, but in the database terms, right, database management system, it is truly called the catalog. So, thank you. Okay, so, right, we described or we changed those, and the database management system is managing that from the catalog or metadata standpoint. Okay, the third one, the implementation of representational models, provides concepts of fall between the two, right? So it's used for this relational modeling that we have, and a lot of times actually when you create these models in the relational type of mode, you can actually feed the model in and it will generate those automatically for you. What's the problem with it generating things automatically?
No control.
No control, and? Okay, so think to all those wonderful pieces of software out there that, oh, just bring this up and you can make your own web page. It's simple. Will it make a web page? Yeah? Will it be an efficient web page? No. Why? Because it puts in all the stuff that you could possibly ever potentially use, because if you don't use it, it ignores it. Right? So they don't want to have to decide what goes in there. They just lump everything in. And what happens to a web page if you have lots of extra stuff that you have to load? It's going to be slower. Right? So, does it make it so everybody can use it? Yes. But if I'm making a application that you feed in a model, I'm going to have to make this generic for everybody to use, so it's probably going to be less efficient. So, every place that I have been at, we have never used any of the generators. We do everything on our own. Right? Okay? So, on the exam, I would expect you to be able to not only list those, but describe them. Yes?
What is the implementation model representing?
Okay, so the conceptual is, again, right, my business customer thinks that there's 15. From the physical, I'm at 550. If I'm really going to take this out and describe it to people from a technical perspective, I'm never going to get through stuff if I have all 550 out there. And I'm not going to cover it very well if I only have 15. So it's kind of the in-between. You're picking out the pieces and making it cover the entire thing, or at least major sections of it, but you're describing it in more detail than conceptual, but less detail than the physical. Right? So again, when I go and take my implementation model and I talk to the other IT teams and the other analytical teams, I don't take the detailed one, right? Because they don't really care, they're not going to access it, but they need to know how I'm doing things. So I want to keep it at a level that they understand the complexity of it, but they don't need to see every last detail, but they have to know that it's way more than, oh, you just got 15, that's nothing. Right, so I have something that's in between for that. So to answer your question? Okay. Right. I always love the self-describing. Mark, I believe we had self-describing code in your programming class. We don't need to put any comments into programs because it is so well coded that it is describing everything that's going on in the program.
I think I did a pretty good job.
You did, but there are some other people in your class that did not. Yeah. Right. So the idea of self-describing is that, combine the descriptions with the data values, right? So XML, right? So key value pairs associated with things, right? Okay. So the idea is that, right? In some ways, we want to be generic, right? But the flip side is, if I say to you, I'm going to build a XML and I'm going to describe it to you because it's very self-describing and it's 8,000 variables long, it's probably not going to be very self-describing. Okay. So in our machine learning models that we are doing right now, we are looking at sending in probably around 32,000 different variables. Giving an XML description is not going to work for them. So, again, all of this works really well when it's small amounts. When you get really big amounts, it gets really tough. All right, so schema versus instances. Okay? So a database schema is the description of the database. So it's describing the structure, the types, and the constraints. Yeah.
How is that different from metadata?
Well, I would say that it's not, in the sense of, right, a database schema is going to describe the structure of a particular database. So here is the structure. Right? Here are the data types that are associated with that particular database. Right? And what are the constraints on a database? Oh, I have a grade field, so you need to be in the domain of grades. Right? Okay. What's in the metadata? The metadata, or the catalog, is the collection of schemas. So the way you want to think about it is the catalog, the metadata is a repository. And the repository inside it is going to have the individual schemas. So they're related in that way. Okay? Okay, any other questions? Okay, so a diagram. Oh, we love diagrams. Because diagrams will always tell you way more than if you try to read something. Okay, so a illustrative display of the most aspects of a schema, right? So you draw it out. Okay, and the construct is a component of the schema, right? So, right? Okay, so it's the pieces themselves, right? So, schema is overall what it's going to be. Schema diagram, a nice picture of it. And the construct is you can pull out the individual components. Right? So just think of it from that perspective. Okay? Right? So, when we think about databases, we have structure on one hand and what's on the other, the actual data itself. Okay? So when we talk about the state of a database, we're talking about what is the data that you have at an actual point in time, right? And it includes all of the data that you have in a database. So, when we talk about databases, they are typically ranging from very static to extremely dynamic. So what would be an example of a static database that we just talked about today? Okay, actually, we've talked about several of them. Okay, if I was to have a grade database, how often do we add or subtract grades that can be given here at school? Probably not very often. Okay. If we think about the buildings here on campus and all of the rooms that are available, right, that we have in here, how often do those change? Not very often, but hey, we got this big construction project, it's going to change all the rooms and all that kind of stuff, right? So it happens, right? Okay, so what about a registration database in the weeks leading up to the semester and the first week or two into the semester? Changing quite a bit. Right? Okay. I have a page that my customers are accessing that is the highest one for me is being accessed with updates about 275,000 times a day. So if I have 275,000, that means, right, my database state has changed 275,000 times in a day. So that's not even counting all the accesses that don't change things. Okay, right? So what we have is instances, right? So an instance is an occurrence of data. Right? So what do we have for each of you in this class? There is a database instance that is out in the registration system that says you are registered for this class in this semester. Right? So Cooper having a instance, right? That's what we're talking about, right? He has an instance. Mark has an instance, right? So they're individual instances and they are different from each other. I could have instances that are unique but used often, right? So I have an instance on the grade database that represents an A+. And I can use that often because it applies to all of you currently. Okay, so the term instance is applied to individual database components, a record, instance, table instance, right? So we use instances all the time, right? So this is one of the really great things about IT is we reuse the same name for all kind of things. So if I just say instance, what are you talking about? The database instance, a record instance, entity instance. What are you talking about? Right? So again, one of our biggest problems that we have from an IT perspective is we are not clear in our communication. So if you say instance, what should you do? You should always preface it with the type of instance that you are referring to, things like that. Okay, so as we said, our database state refers to the content of the database at a particular point in time. Why do we potentially need to know that?
See how it's changing.
See how it's changing? If there's a problem, I can potentially recover to a point in time. Well, what is the point in time that I did a backup of the data? What is the point in time I can recover to? Did it look like at a given point in time, right? There's all kind of things. So when we capture the data that we are processing against the database, it is extremely time dependent. Okay, so initial database state, we have to create a database. So our database can be created and be completely empty. I have what we call load and go databases, where I create it and I immediately load it with a set of data and then I turn it loose to the system. Right, so we have lots of different approaches that we can have associated with this. Okay. And we have valid state, and obviously if we have a valid state, we can also have a invalid state. Okay. So valid state says the state that satisfies the structure and constraints of the database. So everything is wonderful, and if we have a violation of the constraints, then obviously we have a invalid structure. So we have utilities, for example, that we use to scan databases to look for errors and try to fix them. And sometimes we hope for the best. Okay. So when we look at the schema versus state, the database schema should change very infrequently. Okay. So I have a number of my databases that have never changed from a schema perspective since we originally built them in 2003. Because we haven't had a need to. Right? But the state changes every time the database is updated, right? So in my 275,000 times a day, some of those databases that are being accessed there have never changed since 2003 from a structures standpoint, right? Okay, or a schema standpoint, but we are changing it that many times a day. Okay. Right. So we have these schemas called intention and state is called extension. So this is the first book I've ever heard talk about it this way. So it's a really fun fact that you will probably never encounter again, but that's okay. All right, so a schema, right? So what can we look at this? So a student has a name, a number, a class, and a major. A course has name, course number, credit hours, department. We have prerequisites, of course number, right? Prerequisite number, section, grade report, stuff like this, right? And what don't you see on here?
Instances.
You don't see instances. You don't see any data, right? But you know what each of the things or fields that we have associated with each of these databases. Right? So I know that the student has 4 elements, 4 attributes, 4 characteristics, whatever word that you want to put associated with that. Right? So if you remember in the last set of slides when we talked about that catalog of the metadata, we said student had 4 attributes, right? we can list what they are, right? Things like that. So again, this is the type of data that's going to be stored where? In the catalog or the metadata, right? So the database management system is going to use this when it goes to do this processing, right? And the state, right, is now where we're looking at the data. So, right, the key thing to keep in mind here is, what about the shaded rows? They don't really exist in the database. This is just here so you know what they are. But the database management system is going to have to do what? To get to the data, it has to know when you make a request what you want. So it's going to have to go to the catalog or the metadata to say, oh, you want the course number in the course database, so that is going to be the second column. So that's where I want to look for that piece of data. Right? So it's using this metadata or the catalog in your request to then. So again, from their perspective, again, they are not very clear on this, that the shaded ones are there for your reference so you know what they are, but they don't physically exist. Yeah.
Without a catalog, can a database perform any task?
Typically, the database management system will not allow you to do any task without it. Because otherwise, how is it going to know how to interpret it? Now, maybe the Cooper database management system might just kind of randomly do some stuff and see what happens, but probably won't be very effective.
Is it easy to delete a catalog?
It is. And we've actually had that happen. It's great. One of my fun experiences as a database administrator that I will always remember for my entire life is the phone call I got at 5:37 on a Friday night. I know that because I looked at my watch when it rang. And I went, should I answer this or just leave? Because I was literally walking out. Okay, I'll answer. Maybe it's somebody wanting to go out. So instead of going home, I'll be going someplace. Pick it up. We have a problem with the databases. Can I just hang up? No. And literally, the catalog had been deleted, and it took us 5 days to recreate it. So the entire company, because all of the databases were down because you couldn't do anything from the catalog management. So we were able to get a backup of it, but then you had to apply changes that had happened to it and the databases as well, and prove out everything was in place and stuff. So that was the time that I spent the most time at work, because it was literally all day Friday till Tuesday afternoon. And they wouldn't let, of course, they were very smart, they wouldn't let any of us drive home, things like that. So very considerate company. But yes, right, the catalog is literally just a file. Or actually technically a database. And just like you can delete any file on a system if you have the authority to do this. And the interesting thing was, it was an intern that deleted it. Oops. How'd they get access? All right. So a 3 schema architecture. So we're going to take kind of a step back in our scenario here and really just talk about architecture in general, right? So the proposed to support the database management consists of the fact that we have program and data independence, right? So again, your program should be independent of the data. It's certainly going to use data, it's going to store the data, you can access it and all those kinds of things, but it needs to be independent actions. Right? Okay? And we have to support multiple views of the data. So why would we have to support multiple views? Because we have some really sensitive data out there, right? So if I had so like a bank, for example, is going to have your name, your address, your birthday, your social security number, your account numbers, right? Things like that. Well, you don't want everybody to just kind of have access to that and things like that, right? So we create views or ways to look at the data that we can restrict different pieces of it. Okay? What's the good and bad news about that? The good news is that we're protecting the data, but the bad news is now we have to have all these processes, and I end up with potentially multiple copies of the same sets of data that may or may not be in sync with each other. So again, manage that. Okay. Right? So it's not explicitly used in our commercial database management system products, but certainly it's describing from a high level the way that we approach it. So again, a lot of times we take concepts that we have in the general IT world and we apply them differently because of the way that the database management systems are structured, but the concept is basically the same. Okay. So again, we had, if we think of the different levels, right? These kind of tie back to those three that we talked about earlier. Right? So we have that internal schema at the internal level, describe the physical storage structures and access path. So an access path is what is the way that you are going to go to get to the data. So what's the methodology that you're going to use? Right? So if you want to think about it, let's take a step back. And we had indexes. Right? So if I use an index to get to an instance in my database, how's that going to work? You're going to have a program that is going to make a request to the database management system. The database management system is going to say, looking at the metadata or the catalog, it's going to say, look, this is great. I have an index on the things that you happen to be looking up. So let's go look at that index. So we'll go to the index. And it's going to find it. Then what does it have to do? It then has to go to some other completely different location to actually get to the data. So what's happening every time that you are moving around to the metadata, to the index, and then to the data itself? I'm doing an I/O operation on the computer. And what is your program doing while it's going to do all of these different operations? Nothing. You're waiting. Right? So again, indexes can be very helpful, but they also can slow things down. Right? Okay, so again, from our database schema, we're looking at three levels. So the internal one is the physical one, right? So looking at the physical data model. The conceptual schema is at the conceptual level to describe the structure and constraints for the whole database for a community of users. So it uses a conceptual implementation model. So again, those were the two. Right? So I can use either one of those, right? Okay? And the idea here is that, again, the user is not going to be down at the physical level. You're going to want to have them describe things at a higher level and let the database management system convert it to the detail. Right? Okay? And then the external schema at the external level to describe the various user views. So as we said, right, I can have a database that has multiple views that I can access the data in different ways because I have to protect the integrity of the data or the ability to actually view different pieces of the data. Right? So, again, if we go back, right, we talked about the categories of data models. We had 3 of those. And if we come down here, we had the 3 schema architecture. These marks sound like really great exam types of questions. Right? So when I ask to give me 3 of them, make sure you give me the right 3. Okay? So, fair warning. If you get it wrong, it's not my fault.
How come conceptual schema doesn't map to conceptual models? To me, it looks like conceptual schema maps to,
It's conceptual or the implementation. Right? So if we go back, right, when we talked about this one, right, the conceptual and the implementation are that middle layer, that the conceptual one when we're talking about the other set. Right? The physical is the internal layer. The one that is new is the external because now we've added a step outside where I'm restricting access. Okay, is that cleared up?
yeah.
Right? So again, when we come down to this one, right? Conceptual, right? When we look at right here, right? It's conceptual or the implementation, but it's not down to that lowest level. And what do you know about the external one? It's even farther out. Okay, so Cooper, is that okay, or do you?
Yes,
Okay.
yes. It strikes me as sort of behind the wall, there's different levels of technical granularity.
Yes.
And this is in front of the wall.
But we always want to use the same terms in different ways, like we talked about. Right? So kind of the way that if we want to draw it from a picture perspective, right, is what do we have down at the very bottom? We have the actual physical stored database. Right? So that's the lowest level, and that is defined to us, right, from the internal level at the internal schema. So that is defined where? This is what's in the catalog, that metadata. This is describing all of the pieces associated with that. Okay. So at our conceptual level, so that's our conceptual or implementation level, right? That's in between, as we said, right? It's what the user is thinking. More detail from a typically an IT perspective. Here's the complexity that we have around it, but it's not every final detail that's going to be in the metadata. And then going up to the external level, right? The external view to the end user is what they're seeing. Now, the external view can actually be the same, right? So it can be the same all the way down if it's something very simple, right? So if you think of a grade database, right? I'm going to have the grade A+, Cooper's normal grade as the description, right? Okay. Well, the internal schema, the conceptual schema, and the external view is going to be the same all the way up because it's so simple. But if I'm trying to describe an entire application that is in use by the entire company, that's going to have multiple users that have access to different types of data, they're all going to be different. So, Mark, just 2 favorite words in IT? It depends. Right? So they can be the same, but they can be completely different as we work our way up. Okay. So, any questions on the picture? Yeah.
What's the relation between a data model and a schema? How are they used in the real world? Can you give an example of how somebody might talk about those two things in a design process?
We are going to talk about that, and that's actually in the next set of slides. So I'm going to ask you to wait.
Cool.
Okay? And what we are also going to be talking about is the piece that every database class I have ever been in, every set of companies that I have been in have not talked about, and it has cost them every single time. So you will be able to be the rock star of the database world to keep this in mind. So we'll get to that. And if I don't answer it, too bad. I mean, just ask again. But it is a key piece. Because one of our goals is, remember the T word? What's it?
Traceability.
Traceability, right? Right? We need to be able to trace our model that we create from a conceptual model all the way to a physical model. So that's what we're going to be ultimately dealing with. Okay? So our 3 schema architecture, right? Our mappings among the schema levels are needed to transform requests, right? And the data, right? The programs that we have refer to the external schema, map to the database management system to get the internal, right? So we have to somehow get through all those different layers. Right? The data extracted from the internal ones is reformatted to match the end view, right? So, right, the way that we physically store something on the database can be completely different when we display it on a web page, for example, right? So a lot of times we have transformations that are going on as we work our way through processing of the data. And what are we doing with the data? We are turning it into information. Hey, you can say it louder, it's okay. Right. All right, so data independence. So logical data independence is the capacity to change the conceptual schema without having to change the external schemas and the programs. So think about this. Okay? I have 550 databases. I make a change to a database. I add a new field. Am I changing the conceptual schema associated with that and the internal schema? Yes, because I have to add that. I have 40 programs that are not going to that use that database but are not going to use the new field. Do I really want to change all of those? No, right? It's a lot of extra work with no benefit. So that's what we're talking about here, right? Is I want to be able to, from a database perspective, allow ourselves to make changes without having to change every possible thing at the user level. Okay. Okay. And from our physical data independence is the capacity to change the internal without having to change the conceptual. Okay. So, for example, the internal schema may be changed when certain file structures are reorganized, new indexes to improve performance, right? So I am changing something physically in that. I could be changing the size of the database. That doesn't change how all of the things from a conceptual level or the highest level, right, the application programs are accessing it. right? Internal to the workings of the database management system. So we're talking logical level, making changes to the database, but not changing the upper level applications. The physical data independence, making changes to the core database, the way that you're doing things in the metadata, but it doesn't change the conceptual layer of what the users are going to be accessing, the applications are accessing, or what the user ends up with.
The applications, are they, they're going to be more concerned about the conceptual schema.
Yes. Yes. So, right. So again, when you are application person, right? You want to know that you can get this piece of data. You're not concerned where it is physically located in the schema. You just want to know that it's there. Right? Right? So if I want to go to the CIS department and pull up your information, what am I going to ask for? Give me your name or your student number. So I type in your student number, I'm going to get on the screen, here's your name, address, and all that other kind of stuff. Right? I don't care what it looks like or physically, right, in memory. I just want to know when I make the query request to the database, here's the data that I'm going to receive back. Here is the order that's going to come back. Right? So in your queries, as for example, you can return it in a completely different sequence than it's physically stored. Okay? So a couple of the companies I've worked at, their standard was when you retrieve data from a database to display in a screen, the way that you ordered it in the inquiry request was the exact order it would display on the screen, not the order that was on the database. Right? So things like that. So yes, the application needs to know conceptually what's there. It doesn't need to know internally how it's used. Okay, did that answer your question?
Yeah.
Okay. Okay, so when a schema at the lower level is changed, only the mappings between the schema and the upper level schemas need to be changed, right? We fully support the whole idea of independence. Right? Okay, and the highest level ones are completely unchanged because, again, back to the scenario he was just describing, right? They refer to the external schemas, and you haven't changed anything at that level. So again, we try to have as much independence as we can because then, right, it gets back to that idea that you probably talked about in your programming classes of coupling and cohesion, right? So something that is tightly coupled means what? You change one, you have to change the other, and it makes double the work or more. And you don't want to do that. Right? So if it's loosely coupled, yes, they're related, but I can change one and I probably don't have to change the other in most instances. That's what we're trying to get to. So it's really a concept that you guys have all heard about and talked about before, but it's really just a different terminology associated with that. Okay, so like everything else in computer science, our database management systems have languages. And they're great because I can ask you on the exam to describe the languages and all that kind of stuff. Oh, this is just wonderful stuff. Right? All right, so we have the idea of a data definition language and we have data manipulation. And what does the data definition language do? This is shocking. It allows us to describe or define the data. Ding, 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 ding. Excellent. Right? And the data manipulation language allows us to describe how to manipulate the data. All right. So you give me that answer on the exam, I'm not going to take it because it's too simple. Right? All right. So the idea is that, yes, we do have to define the data. Right? So when you think about the data definition language, this is the set of statements that is going to put entries into the metadata or change what's in the metadata. Right? So think about associating the PDL with the metadata. Okay? The data manipulation language is our way of going about and accessing the data to retrieve it, insert it, delete it, right? We're not changing the metadata. We are using the metadata to get there and do it, but it is manipulating the data, not changing the metadata itself. Okay, so our structured query language, or SQL, is the example of something that is a higher level, right, that we can do in terms of our data manipulation language, right? Okay, we have lower level or procedural language, so we embed things inside a programming language to access and do our manipulation. Right. Right. So the data definition language is typically used by your database administrators, your database designers, right? Because again, we are now changing the actual catalog or the metadata, and you don't want anybody just kind of going off and doing that just because they feel like it, right? Okay. And we are also do this, and again, it's typically defined or used by the DBAs to do this, is to create those internal and external views where we are restricting access. Things like that. Okay, so they are called views. Okay. Now we have two other ones that we have in some database management systems. So we have the storage definition language that obviously deals with how we are actually storing the data, right? And we have the view definition language that are to define the internal and external schemas. But in general, the storage definition language and view definition language are just typically defined as part of the overall data definition language and not called out as separate instances. Because again, all of your database management systems typically do the same things. Okay, so our data manipulation language used to specify our database retrievals and updates. We have our data manipulation language commands, or this data sub-language that we can embed in general purpose programming languages, so some host language, so COBOL, C, C++, Java, right, any kind of thing. So I am lucky enough that in my application, all of those wonderful programming languages are listed there. I have embedded SQL in to manipulate our stuff. It's great. And we run it on the mainframe Linux and Windows servers. So I'm accessing the same set of databases from all over the place. It's great. So we have a library of functions that can be provided to access from the different programming languages. And what you have is, for all of these programming languages, you have what's called a pre-compiler. So what was a compiler? It took your COBOL, C, C++, Java, and it compiled it or translated it into the instruction set that can run on your computer. Okay. So that's really great. But now you're embedding stuff like SQL and stuff into your programs. So what does a precompiler do? It looks at your SQL statement or your DML statement, and it converts it into those languages. And then you compile it, and it's all compiling in COBOL or C or C++ or whatever. So it's an additional step that you have to convert to make sure that the languages are all the same before the final compile. Okay, so we can also do DML commands applied directly. So I have a screen that I can get to that I just type in my SQL and hit the submit button, and it magically just executes it, and I get the results back on a screen. I can't use it inside a program, right? But I can certainly view it. We also have the little forms. What fields do you want to see? So you type in the stuff and you hit the button and it plugs those things into the SQL command, it executes it, and again, I get a result, right? So you can run these things kind of independently of embedding it in some sort of program. Okay. Right? So again, it's typically, if you have a relational database, you're doing some sort of SQL associated with it. Right? They tend to be, as we call here, set-oriented. So we're specifying what data to retrieve rather than how to do it. Because where is the how going to happen? The database management system using the catalog or the metadata is going to say, oh, this is what you're requesting. Here's the best way to go about it. Let me go get it. Okay. And it's also called declarative languages. Okay. And we have low-level or procedural language kinds of things. So in these, we go out and we're doing really basic things. So you're getting one record at a time. You're going to process that. You have to go back and request the next one, right? Okay. So we have to keep track of our positioning with pointers and all that, which I know if you had pointers in your programming classes, you just love doing those and can't wait to ever do that again in your entire life. So we mention it because of a single reason, right? Is your high level or your non-procedural languages have restrictions on what you can do. You can only do what they allow you to do. When I had a really low level language, you literally can do a lot more because you have more control over it. Right? So again, you have trade-offs. It's harder to code in a low-level language because, right, you don't have all the predefined things just working for you, but I can do all the things that the upper-level ones don't let me do. So some of ours are actually low-level because we want to do all kinds of internal buffering and all kind of stuff to improve our performance. Because high-level ones typically take longer because of all the extra overhead that they have associated with it. And what do we say everybody's concerned with? Speed. Right? Okay. So, as we said, we have standalone query language interfaces. So we, as we said, we can do SQL queries interactively, right? Okay. We have programming interfaces for embedding the DML in programming languages. So again, you're just taking SQL and embedding those, but each one has a specific format because it has to go through the pre-compiler to actually do the transformation. Right? As we said, we have the user-friendly interfaces. So again, we have forms and graphics things. You fill in the things, click on you want to submit it. It will, in the background, put the components into the SQL that you want done. And the mobile interfaces, right? So you have transactions, mobile apps, and regular apps, things like that, right? So again, what are we really trying to get across here? There's lots of different ways to approach doing this. And what do we say the most important thing is that you have to understand going into all this? What is the data that you have? How is it being used? What way can you get at it? What are the opportunities that you have to do with? Okay, any questions? Okay. All right. So as we said, our programmer interfaces for embedding. So we have the embedded approach. So as we said, you can put SQL for C, C++, all that kind of stuff into the programs. We have a SQLJ version for Java. So again, the idea is you format it in the way that the pre-compiler is going to look at it and be able to convert it into C, C++, COBOL, right? Java, things like that. Okay. So we have a procedure call approach. So this is JDBC for Java, the ODBC, so Open Database Connectivity for other programming languages, having the interfaces. So we actually have both of those in the way that we do things. So I have an embedded approach when I'm running things on the mainframe, and when I'm running on these servers, I am doing the procedure call approach. Right? So again, a lot of this is the programming environment or execution environment that you have is going to determine which way to do this. And because I don't have just a single database management system to work with in my programs, I have to interface to DB2 and to Oracle and to SQL Server and all this stuff all at the same time, and it's really great. Because why would you want to be consistent? Okay. Okay. The database programming language approach. So again, to help programmers, because we know we all need help, right? A lot of database management systems have actually created their own interface. Right? So Oracle has the PL/SQL. It's a programming language based on SQL, so it's to help you do things. But it's not a programming language designed to do all kind of things that all the other programming languages do. It's a really basic one. So even though I have actually taught this in school, I've never seen it used outside of school. So it's really nice. But it's a very, if you want to do certain things that are really simple, that's certainly a way to do it. Right? But the idea is that the database management system is creating these things so you have a self-contained unit. Okay, so you also want to think about, right, so what can you do like in Microsoft Access? You can create forms and build all the things behind the scenes, and you really don't have to ever understand what SQL is to make a database system that is generically working. And you're not going to be able to scale it to any true size, but if you just have some data that you want to manipulate, right? So one of the people on my team loves Access. He will download all of his test files, and he will do all kind of queries to verify all of his test results, because it's just an easy way for him to do that, and it uses the internal building of that. As we also looked at before, we talked about scripting, right? So you have client-side scripting, so PHP, or server-side using Python or some other type of language like that to access and process the database programs. Okay. As we talked about user-friendly, right? So we build, or it comes with the database management system, a menu-based one. You can build forms-based ones. We have graphical-based ones. Right? Typically, the natural language ones where you're writing in written English or some other language don't work very well. So people keep trying that, but it doesn't work so well. We have the really cool voice recognition ones. How well does voice recognition work in your cars? I love when I watch people screaming at their car, because it's not listening to them correctly, right? So we have these, and we're getting better at those, right? But we also certainly have combinations of these as well. Right. Okay, so we have some other interfaces. So again, as we said, you have speech, you have natural language, so you kind of have this free text that ends up being one, keyword searches and things like that. So, and this is really just intended to say there's other ones out there that people are playing around with. Because again, who knows what's going to be popular next? Right? So we're trying to make it as easy as possible for the people who really are never going to know that there's even a database management system in the background. Okay. Now, we have to have, on the flip side, we need a number of utilities that are going to have to function if we're going to actually make all of this work. Okay. So the first one is we have to have some sort of load utility, right? Or the use of data conversion tools. So typically, if I'm going to put data into a database, I don't want to have to sit there and type every one of those in. We only have 4 million records to type in. Let's get started. No, that's not going to work, right? So I can certainly create files. You guys all use 2 files. Create them, and if you define what all of the fields are, you can literally read those in and it will automatically populate the databases. So that's kind of that load and go thing that we have. So every month I have a process that will read through all of the prior month's data. So we run this on the 3rd business day of the month. It goes back, picks up all of the data from the previous month, lays it out in the exact format that the database is in, and at the appointed time, I run the load job that is going to read that data in and add it to the database. And it just runs automatically. Nobody looks at it, right, unless there's a problem associated with it. Okay? All right? Certainly backing up. Now they say putting it on tape, that's very nice, but we have lots of different ways to back up the data, and we will talk about the different ways because there's lots of different approaches. Yes, what are you typically not going to want to do if I have, say, 15 million records on my database? I am not going to want to back up the entire thing. When in the last week, 200,000 records have changed. Right? So we have things like incremental backups. So we'll only back up changes that have happened since the last time that you backed up. Right? So it's going to run faster, it takes less storage and all that kind of stuff. So, right? But then it complicates the recovery if you have to recover, right? So you have to, again, trade-offs, right? Okay, reorganizing the database file structures, right? So again, what is happening if I load data out on my database and I only go out and inquire against it and read it? The data is static, right? So am I going to have to reorganize it? No, right? So I have databases that loaded the data out there and added or deleted a couple things over the years, but I've never reorganized it all. What's happening with that one that I'm making 275,000 updates a day? So I'm deleting stuff, I'm adding stuff, I'm changing stuff, right? So every weekend for that, I need to basically reorganize it so that it's back to its most efficient starting point, and over the course of the week, it degrades. Next weekend, it's great again. Oh, it sucks. It's Friday.
What happens in that reorganization process?
It's what?
What happens in that reorganization process? Because you said that data is getting changed, but you're not changing the definitions of the tables here, right?
No, but what you are changing is physically where the data is stored
But
and
why,
the order that it's stored in.
why do you change that? Why do you change the order of the existing data which is physically stored?
Well, right, so the way that computers work is we store things in essentially what are called blocks. So we have blocks of data, and you specify the size that these blocks are going to be in. And it's important from a database perspective to define these blocks a specific size, because I don't want to waste a bunch of space. Right? So as an example, if my database record is 50 in size, right, and I make it so that my block size, and obviously you wouldn't do this, but I make it 99. I can fit one record in it, and I'm always going to have 49 that is unused every single time. Right? Okay. So now if I block my data so that it's 50 in size and it's 50,000 in total size, I can fit 1,000 of those records in it. Right? But now I want to add something and I'm trying to keep it relatively in order. Well, it doesn't fit there, so I have to put it someplace else. So now if I'm working my way through because I want to sequentially process these things in a batch, oh, in the middle of this block, I have to go out someplace else and then come back. And I go a couple more. Oh, now I gotta go someplace else and come back, right? So my IOs like that are going to slow down the overall process. Or it could be I start off with 50 in the block at the beginning of the week, and at the end of the week, I have 20 because I've deleted stuff. Well, now I want to compress my data so that it makes sense. So it's not I'm changing the structure of the database, my metadata isn't changing, but the way I'm physically storing it and then how I physically access that data can degrade based on where everything ends up from a storage perspective. So does that make sense? Okay. So that's what you're looking at is over time, if nothing's changing, I don't have to reorganize it.
So do you re-index all of the things and reorganize?
You may. It depends on, right? That's why it's the perfect answer, right? But the point being is that depending on how often things are changing, what way they are changing, right? The speed that changes are happening at are all going to play into what way that you have a reorganization process defined. Like I said, I have some that I have never reorganized since I created them in 2003. I have ones, my biggest ones are, I've got them sized efficiently that I can do it once a week. There's other ones that are small, but they're very volatile that I do nightly. Right? And if I have, for example, the instance where I have 8 or 10 different indexes for different ways that people have to come in, I have to reorganize my indexes. I don't have to reorganize my physical data, but I have to reorganize the indexes because of the changes. So that's why I said it's super important for you to understand what data you have, how it's being used, what ways that you're going to be accessing it, the changes that happen over time, because that's all going to play into how you end up designing these things. And there is no one right answer, right? Because in the end, it will always work. It's how efficiently is it going to work? Because I can have a really poorly designed database that will eventually give me the result back, but nobody's going to be happy with it. And the flip side is I can have a really great one that's designed for efficiency, but I have to take it offline so often to keep it at its efficiency that having all of that downtime where users can't access that data because I'm reorganizing it is a detriment to the company. Right? So that's why when we talk about this, there's so many characteristics that you have to consider that a single class like this is not going to be able to cover that kind of stuff. But at least you know about it, so then you can then adjust to it. And that's why I said, right, if you know all of the pieces, then you can, so like for some of mine, we had to experiment because we didn't know what was going to be the best. And it changes over time. So I had some that literally didn't change very often that 5 years later were changing at a regular frequency. So you have to end up adjusting as you go. Okay? Okay, so that fully answer your question? Or you want some more?
Yeah, I'm fine.
Okay.
Yeah, sorry.
See, I talk long enough and that's it. Don't talk anymore. Yes, sir.
So in traditional SQL, do we need to take the database offline while doing this? Because in NoSQL, we don't need to take it offline.
It depends. Right? So again, the scenario is that if I'm taking things offline, I can have dedicated resources to doing, for example, a reorganization, so it's going to get done faster. Because the only thing that is accessing that data or the database itself is the utility. So it's never in contention with anything. I never have to stop and wait because somebody has something out for update and I have to wait for that to complete before I can process that record, things like that. So in general, you can always run these while everything's available, but the trade-off is that you're potentially going to run longer or slower, or you could have a potential that something is corrupt. So I tend to run mine on Saturday or Sunday morning after midnight, because that's when most people are not going to be on the system doing stuff. Right? Where if I look at the pattern of access, one of the favorite times to access my stuff is 2:30 to 3 in the morning. So I'm thinking everybody's coming out from, being out partying late, and they get home and they go, why don't I get on the computer and like buy some stuff? So great sales that way. But so it depends. All right. Performance monitoring. So again, as a database administrator, one of my main jobs was making sure that all of the databases that I was responsible for were performing at the best possible rate that they can. So that means I need to monitor them. So I'm monitoring them not only for speed, but storage locations, size, right? Things like that. Because as we kind of talked, right, adding and deleting things, I could, in one of the databases I had, it would start off at the beginning of every week on one server, and by the end of the week, it would be on 3. Just because of all the adding and deleting and spreading out and stuff, and we would reorganize it at the end of the week, right? But what happens as it expands? My performance slows, right? So I had to keep monitoring it to see what's happening with that. Okay. Obviously, we love reports. IT loves reports and usage characteristics, things like that. Right? Access, functions, sorting, monitoring, data compression, all kind of stuff. So there's all kind of functionality that we have out there. Okay, data dictionaries. So, used to store the schema, definitions, other information, design decisions, application descriptions, user information. Oh, you can have anything you want in a data dictionary. So, what is the good news about a active data dictionary? Accessed by the database management system software, users, your DBA, everybody. And we have the passive kind that's accessed by users and database only. So the difference is obviously the database management system. Okay, so what is the great news about a data dictionary? If you have one, it's got everything you ever wanted to know about any piece of data in any way, in shape or form. It has characteristics about the type of data that you have, the distribution of the data, things like that. And you go, wow, that's really great. I can use maybe 5% of that information. It's really great. Or I can use all of that. That's really great. But what's it take? Time, effort, cost. Right? So, do most companies have a data dictionary? No. Does it cost them? Yes. Costs them a lot. Because what do you want to do? You want to be consistent in the way that you do things. You want all your programs to have the same naming conventions. I want to pick up a program, any program that accesses any one of my 550 databases, and I want to see the same names in every single program. I did this on my application. I actually convinced my boss after 4 years to actually do this, and it cost a project of over $2.5 million to create the data dictionary. Completed that about 4 years ago, and I would estimate today that I have saved $10 million in time. Because everything is consistent. They don't have to look things up, right? We would have situations where I have a sequence of 8 programs, and every single program called it something different. They would always have to go back and verify it's the same thing. What is it, right? They don't have to do that anymore. But it was a lot of work, a lot of time, a lot of effort, but in the end, it saves time. But nobody agrees to do that. Yeah.
What's your estimated yearly cost of maintenance over a data dictionary?
For what?
For maintenance of a data dictionary?
I would, if I was to guess, I've never actually guessed, but I would guess that for my team is currently at 27 people, and I would probably guess that it would be probably $300,000 a year to maintain it, to keep everything up to date. Now, that is adding any new things, right? Any new programs use it, right? That's actually, now that I think about it, probably high. That would probably be the amount of time to access it and use it as well as update it. Because now that I think about it, that's probably the equivalent of 3 people in a year-ish. And that's probably high for maintenance. But I factor it in, right? We just automatically do it now, so. But Cooper, I actually think I had to estimate that when I was making all of my pitches to actually do this, so. Okay, I'll make you a deal, Cooper. Okay, you go and ask somebody about the account, and I will go look up this number and come back to you.
All right.
All right, is that a deal?
Sure. Yeah.
Okay. but you have to go first. Okay. Okay, I'm not spilling my number until you tell me how that goes. Okay.
I get it.
Okay. All right. So data dictionaries work. Nobody wants to spend the money or the time. Nobody wants to do processes. Nobody's going to want to do what I'm going to tell you the super secret is to success. Because it takes time, it takes effort, and nobody wants to do it. But if you have it, you're going to win every time. All right. So other kind of tools, so application development environments and the case tools, right? So we have different environments to build all this stuff out and automatically integrate. All right, so this is an important image, okay? So this is the kind of thing that I'm not going to expect you to draw, but I would expect you to be able to explain any of this. So if we look starting at we'll actually go to the bottom first. Okay, so the bottom is where we have the area of what we call the query and transaction execution. Okay, so this is, if you want to think about it, the core of the database management system. Okay. So the system catalog, the data dictionary, the metadata is in the far left, right? And if you look on that, we have 4 arrows going into and out of this. So guess what? That's why it's really important. Okay? Right? We have in the very middle coming down from the top box, we have our commands, the queries and transactions, and what are those? That's the DDL and DML commands. And it's going to go into the runtime database processor. The processor is going to go access the catalog to make sure that everything is correct, look at the best way to approach it, and it's then going to access the stored data. It's going to go to the stored data manager to process the input and output to the database. And on that dotted line there, we're going to have to deal with the concurrency control. So again, that's multiple people trying to access the same thing at the same time in different ways. Backup and recovery system logging, right? All of the things that we normally have to do with managing the data. So this is going out and physically retrieving the data from the database itself. Yeah.
What does an arrow mean, and why are there 2 different kinds of lines?
All right. So if you think about this, the dash line it's using that data. It's accessing it, and there's data going back and forth, right? But it's not the command itself, right? So I would say it's more along the lines of it's a action that's taking place, but it's not the primary action that they are describing, right? So if you start at the top, right? We have the users being the database staff, our casual users, our application programmers, or our application itself, right? And we have the parameterized users, right? So each one of those, right? So the database staff is going to do the DDL statements. It's going to go through the DDL compiler, and it's ultimately, that's going to go down to the metadata. But that's not going to happen every single time, right? It's when it happens, it's going to do that, right? Okay. If they enter the privileged commands, it's not going to go directly into the metadata. It's going to follow the other path and go down to the command itself, right? So that's the direct path that you're doing, right? And the other kind of scenario is from this is that the requested, an example where you have the DDL statements that are coming in is going into the DDL compiler, right, or the translator, and the output of that, which is different, right? So the dotted dash lines are also showing it's something different. Okay. So the commands come in, it compiles. I have the schema output that the catalog is going to understand, and that's what's going to get moved in. So it's not a direct statement, where the privilege command is going to go directly as it was written into the runtime database processor. Does that help?
Maybe. We'll see.
Okay, so if I'm going to create a database in SQL, I have a create table command, right? That goes into the DDL compiler and is going to look at that, and I don't have in the catalog, I don't have a create command, I have the output of the create command. Right? And it's in the format that's going to go into the metadata data structure that is describing schemas. So that's how it had to get translated from what the DBA typed in from a DDL perspective to what the output of the compiler is. So it's the same thing, but it's translated in between. And that's what's going to go down. So it's dashed because it's different. Is that clear now?
Yeah, I think so.
Okay. All right. So from a casual user perspective, they're doing an interactive query. It's going to go into the query compiler, and it's going to do a translation, right? And because it's doing the verification, right? The query optimizer does what? What's an optimizer? It optimizes things. Negative points on the exam for telling me that, right? Okay, but what's it optimizing? It's optimizing the way that the query is actually going to be executed, right? So what's its connection? It is going to be connecting to look at the metadata. It's not changing the metadata. It is looking at it to say, is there an access path that I can generate that's going to be efficient? Okay, so the query optimizer is adjusting the query itself, then it goes to the runtime database processor and is going to then process the command. Right? From a program perspective, I have the application programs. It's going through that pre-compiler we talked about. Then it does the host language compile. I get the compile transaction. That's what I execute over and over again. Right? So when you have that .exe file, I'm not retranslating the command, the database commands over and over again. I'm just running the program. Okay? So again, the thing that I'm not going to, for example, as I said, I'm not going to ask you to draw this, right? I don't want you to memorize it. But if I ask you what a query compiler does, or an optimizer, or the DML compiler, so I should be able to pick any of these components, and you should be able to describe how they work. Does that make sense, what I'm asking you to be able to recite back to me on the exam? So given that, think about it and make sure that you ask any questions that you want. So, because again, we want to ensure that you retain your A+ grade that you have.
Where did the response back from the database saying that, okay, I have done certain transactions, so is it just not?
It's not depicted on here, but it does go back, you're right. And it's actually going to go through the same process, it's just reversing it. Okay. So your input and output from the databases is going to that kind of stored data manager, right? And the scenario is it can send it directly back out of that, or it will go back through the runtime processor. So different database management systems are structured in different ways, but yes, you are absolutely correct that they don't depict on here, but they really should, that there is a backward path all the way back to ultimately the end user. So whether it's the program, the user, or the DBA, there is some action going backwards in time. Okay. All right. So centralized database management systems. Okay. So it combines everything into a single system. So it's the database management system, hardware, application programs, user interface, processing software. Everything's all located in the same place. Oh, it's wonderful. Okay. So the user can still connect through some remote terminal, however all the processes are a centralized site. So what is the benefit of having everything else centralized? Secure, you have control over it, it's easy to manage. What's the problem? It's all in one place. If something goes down, everybody's down, right? If all the network traffic is coming in and it's overloaded, everybody slows down, right? So once again, trade-offs in the way that we approach it. Right? Okay, so from a centralized organization, right, we have the terminals or the way that the network, so these are facing off to the users. We come into the software, right? The software has the application programs, our terminal, the text editors, all that kind of stuff. And this is where our database management system is going to be, things like that. And ultimately, we have to integrate it all with the operating system and the hardware, right? Because nothing works without the operating system and the hardware, right? So you have all this stuff that ultimately all has to work together to make it all work. But again, the idea from a centralized system is there is only one occurrence of this whole process. Okay? And from a basic perspective, right, you have, right, we have this all over the place in the IT world. So we have print servers and file servers, database servers, web servers, email servers, right? We have all this kind of dedicated centralized stuff in all kind of ways in our world, right? And as a client, you are logging in and you are accessing whichever server you need or a combination of servers in any way that you need to ultimately perform the action that you're expecting to do. Okay. So, right, if we look at it from a logical two-tier, you've got the tier at the top, which is going to be all of the clients. We have the network bus that it goes across, that all the requests are going on, and our requests go to the different servers to get processed from a service perspective as we work our way through. Okay. So our clients, right? So the client's providing the appropriate interfaces through a client software module to access and utilize the various server resources, right? So clients may be system machines, it could be PCs, workstations, right? Whatever you want to access it. And they're going to be connected through some sort of network, whether it's a local network, a wireless, whatever. Okay, and we also have the concept of fat client and thin client. What's a fat client? All of the software and stuff is on the local workstation. And what's the advantage for that? It's all localized and is going to be running on your resources and not have to do the network thing and all that kind of stuff. What's the bad news? If I have to update it or anything, I have to know where it's all and go around it and go to each place and update it and all that kind of stuff, right? It's harder to manage and license and all that other kind of stuff. What's a thin client? Everything is kind of web-based or form-based, and I just access the stuff and we go to the client servers and run everything in the background. So, what does that mean? My software and my data and everything is managed at one server and everybody accesses it. Problem is, if it's down, everybody's down. Right? So, again, trade-offs as we look. So, from our database management system, server provides the database query and transaction services to the clients. Our relational database management servers are often called SQL servers, query servers, transaction servers, right? Some kind of name. Again, we're not very standardized in the way that we do things. Applications running on our clients use the application program interface or APIs to access the server databases, right? And again, we talked about two of those being the ODBC and JDBC for access and execution. Okay. Our client and server must install the appropriate client module and server thing to access that, right? We connect to several different database management systems, being our data sources. So again, like I said, my applications run against multiple database management systems. We have to integrate them all because they're not my data source. They're owned by other people, but I have to access them and use that data. Okay? So data sources can be files or other database management systems, right, that manages data. So again, it's not always pure databases, but I have privileged databases that are proprietary to different programming languages. So as I said, an example is our SAS ones, which are statistical ones that they have a proprietary database format. So we have database programming. So again, kind of the idea associated with that is, right, we have to integrate our database changes or our database accesses within the programming languages that we're doing from an application standpoint. Okay. So if we go to a 3-tier architecture, right, so this is what's common for our web applications. So we have a intermediate layer being the application server or web server, right? So it's managing the web connectivity and business logic, and it's the conduit for sending partially processed data between the database and the client. So again, we've added something to handle the manipulation of the data and applying the specific business rules, and then applying the web connectivity point associated with that. Okay. So the actual reason a lot of times we don't do the 2-tier, but we go to the 3-tier is for security. Okay? So if I can potentially get to the middle tier, right, I have to still get access to the 3rd tier, right, the database tier, right? If I don't have the proper authority, I don't really care whether you can get to the business logic, right, or not. If you can't get to the data, you're not going to be more secure. Right? So things like that. Okay. So the clients cannot directly access the database server. So again, right, if you can't directly access it, right, so a lot of times what we have is you have the external use by the clients, right? So they have their machine, they access a public-facing server, right? That is open to the public, right? But they can get through the firewall to the database server, right? But it's only through that. So again, you have another layer that I can deal with. Right? Okay. The clients contain the interfaces and browsers. Client, as you said, is typically a PC or mobile device, right? But again, you typically go through 3 layers, and the important piece of the database and the database data that you're trying to secure is in the innermost spot. Okay. So if we look at a picture of this, we have the database management system and the database services layer down at the bottom. We have the application programs, the web pages, and the business logic in the middle, and we have the presentation or the interfaces that you have that are facing the user at the top, facing the client. All right, so if we talk about classifications of our database management system, we have 3, because you're always going to, right, so on the exam, what are you going to remember?
3.
Every answer has 3 parts. Right? Right? So in this case, we have legacy, which is that kind of network and hierarchical piece that we talked about. Right? Legacy is still in existence from a hierarchy perspective. I don't know of any place that uses network. But again, hierarchy, if you need something that's extremely fast, that's the one that is going to be most beneficial if you're not using something outside of the high performance ones like Hadoop. If you're using standard databases. So relational, object-oriented, object-relational. Again, out of those, you're going to typically find relational is going to be the one that is most used out of this grouping. And as I said, we are still evolving on a lot of the other ones, being the key value storage system. So that's the XML type of process. Okay. Document based, things like that. So, right, and then our other ones, right? So single user versus multi-user, right? So again, Microsoft Access is going to come as part of Microsoft Office, so it's going to be on your workstation, right? So it's personalized, and multi-user is the most of the database management system that you can have because it's going to be associated with putting it on a server for. And again, the large databases that you have. Okay, we talked about centralized versus distributed, right? So centralized, again, we use a single computer with one or more databases, but they're all located on the server itself or on the computer itself. Distributed, multiple computers, multiple databases, things like that. So what would be an example of where I would want something to be distributed as opposed to centralized? Okay, so I have, not me, actually Mark. Mark has a company. And he's got warehouses around the world because you have a global company. So, at the Faro World Headquarters, right? In what?
In Ypsilanti, Michigan.
In Ypsilanti, Michigan, right? Right? Everything has to go through this central spot. Whether anywhere in the world, it has to come to that one spot, right? But what do we know? All of his warehouses and distribution centers are really only concerned with what they have in their world. So, what Mark decided to do to enhance all of his employees' satisfaction, because they were angry with the slow speed of his computer system, was he distributed them so that it's treated for Mark as a big, large database. But each of the distributed pieces were at each of his warehouse distribution centers. And they accessed their own database management system, their own set of data, and it was faster. Now, Mark, being the good guy that he is, sucked up the fact that his stuff was going to be slower because it had to go to all the places to get everything from a corporate perspective, but the day-to-day operations were better. So we have that a lot when we have pockets of data that are useful in only one location. But we still want to tie them all together as one unit, right? So we distribute it, but it's overall still considered one. Okay. So we have homogeneous distributed database management systems, right? So what's homogeneous mean? They're all the same, so Mark's thing is the same all over the place, right? What about heterogeneous? Is different, but it's in different places, but it's still considered one big giant one, right? We have federated or multi-database systems, so this is falls into the distributed we just talked about. So persisting databases are loosely coupled with a high degree of autonomy. So again, all of Mark's locations are independently working, but they are coupled together from his viewpoint when he tries to get it all together. Okay, so your distributed database systems have now come to be known as client-server-based database systems because they do not support a totally distributed environment, but a set of servers facing off to a set of requirements. So again, the point that we're just trying to make with this one, and I'm not going to ask this kind of thing on the exam, right? But the idea here is that we have a lot of these things that overlap, right? So in this case, we're saying that we have distributed, client-server, right? So yes, we can, depending on what your view is, come up with different definitions, but we're not going to worry about it. Okay, so costs. Free open source to millions of dollars. Marx is millions of dollars because he had money to spend, right? So MySQL, things like that are all in the free category. We have time series, we have special ones that are specific to certain categories, so of course they're going to charge you for those, right? So right, we have the idea of different ways of storing all of the data, right? So different storage technologies are going to fit into this. You have different licensing, right? It's just a monster trying to manage this. That's why Mark farmed that out of all the contracts and stuff. So, point is that a lot of companies are spending a lot of money on these things, especially if you end up having not one but multiples. Right? So, like I said, right, I have to deal with Teradata, I have to deal with DB2, I have to deal with SQL Server, I have to deal with Oracle, and licensing and for every single one of those, and paying for it. And I'm sure it made sense at one point in time, but oh, now we have Hadoop and stuff, so like even more, so it's really great. So, with that, have a great night. Oh, I know it was so much fun, Cooper, that you wanted to just stay for like another few hours or something.
You have a great night too.
Thank you.